So, in the last few lectures I have been discussing about the growth forms of solidification, and in the latter part of the last lecture I told you how we can deal with alloys. So, in fact in today's lectures we are going to describe how solid partitioning during solidification of alloys takes important role in deciding even the growth forms. So, first let me tell you that whenever we discuss about alloys, we all need to know phase diagrams, because phase diagrams will tell about the equilibrium behavior of the alloys. So, we start with the equilibrium solidification, then slowly relax the equilibrium conditions and show you how actual conditions or real conditions will affect different growth morphologies. So, first let me discuss with you about the solidification of a bar under equilibrium condition. Suppose if I have a bar of this kind of shape and I want to solidify, this bar contains an alloy with certain amount of solids. Okay. So, I just keep this phase diagram picture on the right side, which I have drawn in the last class also, to make you understand things very clearly. Little bit modification of these aspect as far as the composition axes are concerned. Okay, so we are talking about solidification of an alloy with composition Xp0, that is in between the solid and liquid. So, this is alpha, this is liquid plus alpha, and there is a eutectic composition. You see this eutectic composition Xpe, and this is the maximum composition of the solute which can be there in the alpha phase. So, upon knowing a little bit of idea about the phase diagrams, let us now consider an alloy of composition Xp0 which we are solidifying from the left side, that is from this side to this side. What I am going to plot is basically composition, that is Xb as a function of distance x. Okay, this is x. So, when a small amount of liquid solidifies and major part of the liquid has not yet solidified, how the composition profile will look like, how the compositions of the solute B will in the solid and the liquid will vary. Let us see that. As you know, I have already defined a term called partition coefficient, that is equal to K. K is nothing but Xps divided by Xpl, that is the compositions of the solid divided by the composition of the liquid. Sometimes this can be also written as Xp alpha by Xpl when alpha is a solid phase. So, this is a fraction in this phase diagram, it is always less than or equal to 1. Maximum value can be 0.99, but mostly it is a fraction. Now, the first solid which will form, as you see here, is basically having a composition given by these, which I have discussed in the last class. We will not go back again. So, therefore, if I draw and if I write this is Kxb0, Kxb0 is the solid composition. As you know, if Xb0 is the liquid composition, then if I put it Xb0 here, solid composition will be Kxb0, and this is suppose my Xb0 point, this point. So, what will happen? It will solid will have, because equilibrium case we are discussing equilibrium solidification, solid will have uniform compositions, then it will rise and it will remain Xp0 all throughout the liquid, right. It is better actually plot using a color chalk. This is what is happen under equilibrium condition, am I right. So, solid which will form at the beginning first will have a composition of Kxp0, where the liquid has a composition of Xb0 all throughout. Now, if I solidify little more, what will happen? Suppose if I solidify same bar half, the hatch side is solid and this one is liquid. So, again let us plot the composition versus distance. Okay, this is Xp versus distance, and this is my solid liquid interface. So, I have made a dotted line here. So, what will happen is very simple, and this is again Kb0, because equilibrium case means this is Xp0 again Xp0, and this is Xpl, right. Xpl is the any compositions in the liquid. So, obviously this will go and increase as you look at it, this will go and increase to Xp0 here, and then it will remain Xpl, because a liquid will have more compositions as far as these solid partition is concerned. As you see here, if I have some are there, so this is my Xpl, this is Xp0, and this is my Xp1 suppose. But initial solid has Kxp0, but because we are doing an equilibrium conditions, this compositional difference will be completely annulled out. So, initially although there will be little bit of post problem, but it will go back and remain like this, okay. Slowly it will catch up. So, that means what? Solid will have always uniform composition of Xp0, okay, always. Okay, now let us do it for the completely solidified block. Again this is distance x, this is Xp, okay. So, Kxp0, Xp0 and Xpl. Because it is completely solidified, we are talking about equilibrium situation. So, it will be flat line with a composition Xp0. That is what will happen in the equilibrium under equilibrium conditions. So, let me write down, this is equilibrium, that is better to write. Now, as you know, equilibrium condition is like an ideal condition, it never prevails in the actual experimental conditions. So, we have to think how far we can go away from the equilibrium. So, one such situation is that complete diffusion in liquid, but limited diffusion in solid. We are going to deal with that. What does it mean? That means that because liquid has diffusivity 3 orders of magnitude higher than the solid, so anything which is getting rejected in the liquid will be uniformly adjusted, right. On the other hand, in the solid there is a problem of diffusion, because diffusivity in solid is very low, and because of this low diffusivity in the solid, we are going to have a situation where diffusion will be very limited. If that is what happens, then how things will look like? It will, let me tell you, that things will be completely distinctly different. So, I am going to draw it for you purpose. Obviously, first thing, the beginning of solidification will be similar as compared to same as the equilibrium. So, remember this is Kb0, Kxp0, this is Xp0, okay. So, and that means what? This will be almost similar, it will not change much. This is my interface. Let me draw it with color chalk, little bit slope will develop here, then this will remain like this. Things will start changing, that is mainly because diffusion in the liquid is uniform, that is why the liquid composition is same all throughout, but diffusion in the solid is not uniform. That is why you see the solid composition at the beginning it was Kxp0, then slowly rises. There is a small rise because of these limited diffusion in the liquid solid. So once you do that for the next thing, that is half solidified, again Kxp0, Xb0 and Xpl, suppose here. So this is my interface. So how things will happen? Things will be happen like this. I'm sorry, let us use the chalk. Things will happen like this. It's very clear again that liquid has uniform composition, because liquid has no diffusion problem, its complete diffusion is possible, but solid has a compositional difference. That is what is the coring we discussed in the last lecture, that different parts of solid has different compositions, and that is mainly following the phase diagram. As you see here, if I draw these style lines, this is what is going to happen. If I draw these vertical lines, so you have 1, 2, 3, 4, 5, 6 different compositions, and that is what we plot. This looks like this. Okay, so it goes at the interface. It obviously there has to be a jump, because solid and liquid compositions are distinctly different. Liquid compositions followed by the liquid as. So these are the ones. So at the interface there is a huge jump as compared to solid compositions. So that is understandable. Now let us look at what happens when it is completely solidified. When it is completely solidified, again Kxp0, point Xb0, Xbl, okay, and I am just drawing a dotted line across the Xp0. So what will happen? This will be like this. It is very clear, solid will have different compositions as a function of positions, you see here, and finally it reaches Xp0 at a later part of these, you can see here, later part of that, and its composition shoots up, because see the area under this curve, whatever is lost here, solute in the solid, must be same as whatever is the area under this curve, okay, because we cannot destroy solids, okay, that is what it is. So therefore there will be huge composition spike at the end of the sample. So let me just do the third situation, which is very important. We will discuss each of these cases today, and that is the part of the 2 lectures. So if I have another situation where I have limited diffusion in both in solid and liquid, what does it mean? That means that obviously limited diffusion solid is acceptable, in the sense that solid has a very low diffusivity. Diffusivity of the solute in the solid is low compared to the liquid, in fact 3 orders of magnitude difference. But suppose in the liquid also we have problem of diffusion, that means there is no convection present, or there is basically diffusivity of this species which is moving in the solid basically is also low compared to normally what we get. So because of that we can have a situation that both diffusion in the solid and liquid will be limited. Then how things will look like? Things will be completely different, okay, as we have seen here. The major difference will be in the sense of mostly in the second and third part. So first part it will be almost similar, there will not much change, Kxp0, Xp0, okay. So this is my interface, I am drawing this thing. So this is what it will look like, not much difference, but things will be different here in the intermediate stage. So Xp0, Kxp0, Xpl, this is Xpl, please always refer the phase diagram. As you see the compositions, these are relative values. So how it will look like? It will be like this, then there will be spike, because in the liquid there is there is limited diffusion in the liquid. So whatever solid is getting rejected in the liquid will be piled up at the interface. That's what, oh sorry, we have done the interface little, it should be little ahead. Interface is here, right. The curve, nature of the curve will remain same. So in the solid, because of limited diffusion, the composition will be looking like exactly same as that, but in the liquid it will no longer even flat, it will be like a pile up. At the interface there is a solid pile up, because, and the reason is very simple, liquid has limited diffusion, there is no convection, so because of that there is a pile up, and this pile up is basically the reason for creating such a spike of the solid profile at the interface. Now what will happen when you are at the end of the solidification? That is not very difficult to understand, there will be huge spike at the end. Okay. So this is kxp0, so it will be going like this, and at the end it will reach to xbe, that is the xbe is here. Okay, you see that xbe is at the, in the phase diagram it is almost at the end. Okay, here this is the xbe, this is xpl. So we are much higher than the xpl. So this is what is going to happen. Okay, but remember this is the more generalistic situation which we observe in the real materials when you solidify. So now question is this, for solid distribution of such a kind of stuff we can easily use a lever rule, okay, the equilibrium situation. Lever rule can be applied. So what is the lever rule? Lever rule says xb0 is the base composition, thus multiplied by, suppose, fraction of the solid, fraction of solid multiplied by solid composition plus fraction of liquid multiplied by composition of the liquid. Mass balance must be retained, correct? This is the original alloy compositions, thus must be equal to mass or the total composition of the solid multiplied by total composition of the liquid. How do you get total composition of solid? Fraction of the part which is solidified at each cases multiplied by the composition of the solid plus fraction of the liquid in cases multiplied by the fraction of the solid, that is the composition of the solid liquid in each cases. That is how it is. This is called equilibrium lever rule in the literature. Now for second situation we need to derive the rule, okay. As you see clearly for the second situations, at any time what is happening? At any time, because of limited diffusion in the solid, okay, there is a difference of compositions, and that difference of composition leads to change in the material, change in the balance. So let me do it for you. So very simple, let us suppose we have, what shall I do? Let us, we have to go to that side of the board, okay, that is the problem. So I remove this phase diagram. So suppose I have dfs is the fraction of the solid formed, okay, this, because of formation of this there is a difference, there is a solid change, and solid composition difference is basically in the liquid minus solid, that is my difference of the solid multiplied by the fraction solid which is formed, that is the dfs, must be equal to the rise of the solid, let us write down S and F as a superscript, multiplied by change in the composition of the solid in the liquid, because whatever has been rejected by the solid because of this composition, these kind of things happening here, because of that there is a rejection in the solid, okay. So remember this composition is higher than the xp0, because there is a build up or there is an increase in the liquid. So this is the increase, this is the delta dxl, and the fraction of the liquid, how much liquid is left over, that must be multiplied with that. So this is the solid rejected into the liquid, and this rejection is equal to the change in the solute concentration in the liquid. Now we know that K is equal to XPS divided by XPL. This is a partition coefficient, right? So therefore we can modify this, and we also know that FL is equal to 1 minus FS, very clearly we know that. So let us make change over the DFS, so XPL, XPS, so I will change XPS, so XPL minus K XPL, XPS equal to K XPL equal to 1 minus Fs into D XPL, right. So you get a very nice differential equation. So now we can differentiate, we can integrate rather, DFS 1 minus Fs, I can take out Fs there, and dxpl is equal to 1 minus k xpl. That is my differential equation, okay, solid balance basically. So if I integrate that, I will not do it full, you should do it yourself. So I will simply write down the condition, the boundary condition. The boundary condition here is this, that when Fs equal to 0, that means when there is no solid, Fs equal to 0, that means this one's solid vanishes. Remember Xps is equal to Kxb0, right. Very simple. When there is starting of solidification, at the beginning of solidification, solid fraction is very small, so therefore it is equal to 0. The composition of the solid will be Kxb0. That is the first solid which forms will be equal to Kxb0, and this all Xbl is obviously not required, that is equal to Xb0, that will be also equal to Xb0. So if you plug in all these things, the final equation I write down here is will be Xps equal to Kxp0 1 minus Fs to the power k minus 1, and this one is known as equilibrium lever rule or non-equilibrium lever rule or Shell's equation. Many people say Shell's equation. Is it clear? This is very easy actually, anybody can do. Only thing we are doing is the solid balance, both in the solid and in the liquid. Because of the limited diffusion in the solid, we need to take care of this balance. Now this problem, when you have a limited diffusion in solid and liquid, is very long thing to solve, and I will not solve it in detail because that will take a lot of time of mine. So but I urge you to look in the book. Basically this is nothing but a diffusion problem. The equation which we can use to solve this thing, the reason I am giving you this mathematical part is that you can practice yourself from the book, as well also you can actually solve problems which will be part of your assignments in the books. So for this situation, the equation which is basically can be used is very diffusion equation which you have already used. Okay, let me write down that. In the liquid we can write down, because things are happening in the liquid, remember. Things are happening in the liquid, okay. You can see here there is a spike formation in the liquid, then things happen. So this is what the more generalistic picture, the spike, the solid built up in the liquid. So this is, we can write down a time dependent diffusion equation, that is very easy. TL in the space and time, take small x is the space, capital S, when you have superscript, subscript, that tells you the composition, the small t is the time, plus v is the velocity of the interface. This will be, remember this is my diffusion equation, we do not have this term, the third term on the right side of the diffusion equation. That has to be built in here because interface is moving, it is not a stationary interface. As you see here, as you start solidifying, this interface is slowly moving from the left to the right. So this interface movement will also change the solid balance, that is taken care here in this part. Okay, so first thing one can do is that we can assume steady state. So we can write down dB dxlb tt 0, and then the solution of this equation is very easy. That is what normally is done in the book. If I want to take the solution of the time dependent part of the equation, that is basically very cumbersome. It is there in the books, in many of the books, but that is very cumbersome, that is not required. We can always assume the steady states arrived here also, because these profiles are drawn once steady state has been reached. So finally, if I do that solve that equation, what I can get? I can get XPL, right? I can get XPL. Basically, it will be solution will be very simple, very easy. It will be A exponential minus B by DL x plus B, where B, A and B are constants. You can see that. The second order differential equations. So dx2 by this is equal to minus B by DL multiplied by that. Okay, so that then you can assume the solution of this equation is exponential kind of a solution, and you can do that. It's there in the standard mathematics books. So to find, you can find out these conditions A and B by using proper boundary conditions. Then it will be become xb0 1 plus 1 minus k divided by k exponential minus b by dl x. That is what will be the actual solution for this third case. And anyway, similarly you can write down xps also. Xps will be multiplied by, basically divide by xbs is what? Xbs is equal to xbl divided by k. No, k multiplied by xbl. So this will go, k will go down and it will be there. So that is basically very important aspects. So as you see here, these three situations which I have done, I have discussed as a part of this discussion on this growth and solidification for alloys, is what is generic, very generic situations. This will be taught even in the solidification of different alloys also. So we can logically understand these aspects as I discussed with you. We can also do mathematical equations, formalisms to understand that. So finally, the third situation is most common in the alloy solidification. We normally do not have sufficient convection in the liquid to have uniform composition of the solids in the liquid. We will have always such a kind of spike in the compositional profile, and this spike is very important for the formation of dendrites in the alloy cases. So in the next lecture, which I will discuss how the dendrites will form and how we can actually use a novel theory to explain the dendritic formation in the alloys.